I am thrilled now to announce Dr. Kerry Kingham. We're thrilled to have you, please.
Well, tonight I'm going to talk about the basics of HF propagation. Some of you may remember that I gave a talk before a field day about field day propagation. And this is just a generalized version of that and with a couple of wrinkles. And I'm going to talk about, well, that's good. I'm only going to consider the HF frequencies, 3 megahertz to 30 megahertz. That's the 80 through 10 meter amateur bands. 160 is medium frequencies and has some really weird things. And the 6 meter band is really low VHF. It's the magic band. You all know that. I'm going to consider propagation only by line of sight or via the ionosphere. We'll not consider ducting, tropospheric bending, or scattering. And the important thing, one of the important things to remember is that radio waves are refracted. They're not reflected. When they go up and hit the ionosphere area, the change in charges that they come across causes it to bend. So the radio waves are not bouncing off, they're bending. And you have to have a density change, and that includes things like ducting tropospheric bending or charged particles, which is the ionosphere. This is like when you look at a glass with something in it and you see the pencil or whatever is broken by the optics. It's the same thing, only using radio waves and charged particles. And charged particles are created by knocking electrons or ions off of neutral atoms or molecules. And the important thing here is electron density. That's because there are more electrons than protons, and that's the density of those is what causes the bending. And it doesn't happen low in the atmosphere because the atmosphere and the material is so close together that recombination happens immediately. So there's no time to have an electron floating around. It recombines to the atom right away, and you don't get any free electrons floating around. And as the density of atoms decreases as you go up in the atmosphere, then you get to a point where these free electrons can hang around for an appreciable amount of time. And that's where you get the effects and the refraction. And so you're limited in that direction by too low density because you don't have any particles, or they're too far apart is the main thing. This is first diagram of 3, I think, on the ionosphere. This shows a transmitter with radio waves coming off in different takeoff angles. And depending upon the takeoff angles, it depends upon or determines what happens to them. The vertical ones, I have to say one thing, which is that the D layer is entirely absorption. There's no bending and refracting back to the surface on the D layer. It just absorbs the radio waves in the HF. So you have to get through the D layer, and that becomes an important consideration. The E layer and the F layer, however, can bend the radio waves, but the major one that we're going to consider here is, until later, is the F layer, which is the main one which handles high frequency propagation, or where you can talk to somebody around the world on 10 meters with 10 watts. The transmitter, when the radio the second thing that you have to remember is that the amount of bending has to do with the angle of incidence, and as well as the electron density and the frequency. So if you fire a 10 meter signal straight up, it's going to go right through the D layer, it's going to go right through the E layer, it's going to go right through the F layer and say bye-bye. and you don't get anything out of that. On the other hand, if you send a 10-meter signal at a low angle, it has to travel more through each of the layers, so it sees more electrons as it goes through, and at each bit of that density causes it to bend, and eventually it bends and comes back to the ground. And this can happen straight up if you fire slightly off of straight up with a 40 meter or 80 meter signal in the daytime, it'll go straight up, it'll hit the F layer, and if the F layer is thick enough, it'll bend that signal all the way around and it'll come back down. And this is called near vertical incidence propagation, or usually NVIS is the term, and it's a way in which you can use high frequency, which often doesn't, as we'll get to here, come back locally. That it'll come back locally, and you can talk to somebody nearby. And in fact, in Hurricane Maria in Puerto Rico has mountains down the middle and has most of the people living on the coast. And if you're on one side of the island, you can't talk to the other side of the island when all your infrastructure has been wiped out. So FEMA and the hams down there used NVIS. They fired the signal up. It went up in the air. It sort of fountains and comes back down, and it comes back down on the other side of the mountains. And so they were keeping all of their emergency centers hooked together by NVIS communications. And as you see here, you have critical angles, and you have the Earth. So your transmission that actually goes somewhere for DX, for example, you have the critical angle where the bending is enough to bend the signal back down. And then you have the problem that you can't go through obstructions on the ground. So it gets blocked, and that's the bottom. And normally, and also the way your antennas work, normally in a ham radio, you figure somewhere around 3 to 5 degrees is the lowest that you get signals going out that are going to go somewhere. Here's another diagram of similar, that's similar, but this one is concentrating on the fact that when the signal goes up to the ionosphere and gets bent back, there's an area in the middle that doesn't have a signal. So you get a certain range of takeoff angles that come back down to the ground, but between you and where they come back down, there's nothing. So you have what is called a skip zone. You get no signal in that area, and you can get a second bounce off the ground up again in the second hop and get a second signal. And because of the fact that things sort of spreading out when they do that, you get a bigger area that's covered in the second hop, but it's also a lot weaker. So there's a trade-off. Okay, this is a diagram. This is going to be important later on. The D region, the D layer and the E layer start somewhere between 50 and 70 kilometers above the surface of the Earth. The D layer goes up around 90. The E layer can go up to almost 200. The F region starts at about 160 and goes up to about 400 kilometers. And that's why we like F propagation, because it's higher up and it gives you more distance when your signal gets up in the ionosphere, gets bent, and comes back down. And this is the importance for these heights, is that it has to do with when you have other factors going on, such as Aurora and Sporadic E, which we'll cover later. So in the normal sun, the ionosphere is affected by the radiation coming from the sun. And the extreme ultraviolet gets to the upper layers of our atmosphere. It interacts with the upper layers of our atmosphere and causes free electrons to be knocked off of atomic hydrogen. And that's the F layer. The X-ray, soft X-ray and far ultraviolet gets a little further down in the atmosphere, and that they knock off they knock electrons off of molecular oxygen, and that causes the E layer. And then mostly the X-rays come down through all of this and get down to the D layer, and they knock off the most common material in the atmosphere: nitrogen molecules, oxygen molecules, and NO, nitrogen and nitrogen. Is that nitrous oxide or something like that? And I'm not a chemist. Anyway, so that's how the layers form. And the important thing about this is, as I mentioned before in another diagram of the ionosphere, at night, because these regions are pumped to get the electrons, to boil the electrons off by the solar radiation, when you don't have solar radiation, they start recombining. And in the case of the D layer and the E layer, they recombine very rapidly. And when they recombine rapidly, the layer disappears. So the D layer and the E layer, for the most part, are only daytime layers. They do not exist at night. That's important because the D layer is your major absorber. That is, the radio waves going through the D layer get absorbed and they don't get through very well, and it goes away at night. That means that frequencies that are absorption dominated, that is the lower frequencies, get absorbed, and only the upper frequencies can get through. So that's an important thing. Also, the F layer, which in the daytime splits into the F1 and F2 layers, at night they combine in a single F layer. So you don't have the two F layers causing refraction. So, but this isn't the whole story. The solar, wind, and other active regions on the sun accelerate particles and send them across space from the sun to us. And these particles also interact with the upper atmosphere. And the difference is that the particles being having, for the most part, magnetic fields or being charged, interact with the Earth's magnetic field. And those of you who have taken physics know that when you have magnetic field and electric field, and one of them, and they're moving, one of them's moving, in this case the electrons, when the electrons are moving through the magnetic field, they get bent around and they actually start spiraling in the Earth's magnetic field. And that right there causes some problems. So this is an active sun, and it's just to demonstrate, to show the fact that sometimes there's lots of stuff going on in the sun, and everything you see that's bright there is a place where materials is leaving the solar gravity and traveling out in space, and the stuff that's pointed towards us will eventually hit us. So active regions, which is where a lot of these particles come from, are places in the sun where the magnetic fields are tangled. And this happens mostly at solar maximum, but it can happen at any time. But they get very, very active, and you get a lot of tangled magnetic fields near solar maximum. And one of the things that happens is you get these spiraling electrons in the sun. Now we're talking about the sun, not the Earth. When you get them forming on the sun, you get a thing called a flux tube. And a flux tube, this is a good shot of a flux tube. A flux tube forms above the photosphere of the sun in a lower density region of the sun. And because of the magnetic field and because of the charged particles, they're all going around and around. And this can actually generate its own magnetic field and become self-supporting. And it sits there until the energy supply gets cut off, which usually is due to something called magnetic mirrors, which we'll talk about a little bit about later on. And then it's sitting there. It has no new energy coming in. It's sort of self-supporting, but of course it's radiating and it's losing energy, and eventually it collapses. And depending upon how it collapses, depends upon what comes out. And you can either it can either sort of go and go away. If it comes down a little harder, it'll flash, give off a lot of energy at once and cause a flash. And that's what we call a solar flare. And then if it's really got a lot of energy, it'll actually accelerate all the material above it and push it up and out of the sun. And that's called a coronal mass. Yeah, it's a coronal mass ejection, coronal mass ejection, CME. So in the high solar activity, you've got more charged particles coming to us because of the material that's being thrown off of the sun, traveling across space and coming in on the Earth. And you get the F layer can get denser and able to maintain bending at higher frequencies. So you can actually get 6 meter and 2 meter and maybe even higher if you have a heavy hit on the F layer. You can get some enhancement of the D layer because the X-rays that get created, particularly by the flares. And so you get increased in absorption, but you only get that during the daytime. And you do get DX enhancement at higher frequencies than at night. So you also get things like Aurora. You get and you get geomagnetic storms. This particular slide's a little confused, but you end up with geomagnetic storms happening because you're disrupting this material coming in is disrupting the Earth's magnetic field because it's on the order of magnitude of the Earth's magnetic field. The Earth's magnetic field, by the way, is very weak, but it does a really good job of protecting us, even so. So if you have a solar flare, when that flux tube collapses, you get a recombination and you get emission of everything from gamma rays to radio. You get no warning because it travels the speed of light. So anything that would warn you, the signal gets here at the same time that the flare gets here. And it's not because it's radiation mostly, it's not affected by the Earth's magnetic field, so it comes straight through. And this is the white area on the lower left there is a solar flare. And then you get all sorts of strange things when that stuff hits. Remember, this is really high energy stuff hitting the top of the Earth's atmosphere and the ionosphere. And you get, you can open the ionosphere to more charged particles, because basically the way the ionosphere protects the Earth is that things hit the ionosphere and cause it to ionize and takes the energy away. Well, if you take all the energy out because you're hitting it really hard, there's nothing there to absorb the material coming in. You get those ions that are there coming down, like from solar wind or from other solar activity. They find it easier going down through the ionosphere because there's less magnetic shielding. And you get physical collisions and chemical reactions. And basically, everything's enhanced because you get secondary physics in the upper atmosphere that generates X-rays. The F layer can disappear because there's no electrons left. But one of the main things is the D layer is enhanced because all of this stuff comes right through, hits the D layer, ionizes the O2 and N2, which take a lot to ionize, and the absorption goes way up, propagation disappears. You can't get anything through. So solar flares are the main effect of solar flares on radio is that signals disappear. And I've been at a field day in which we had a solar flare. We thought the radio died because suddenly there was nothing there. And the thing about a solar flare though is that it takes about an hour for the recombination to start occurring again. So a solar flare lasts for about an hour. The effects of a solar flare last for about an hour, and then it starts coming back. And because of the way things work, and because it's the D layer that's causing all the absorption, your higher frequencies come back first. So if you are somewhere and you think there's a solar flare, or you get an alert that there's a solar flare, you might try the higher frequencies first when it comes back. Okay, now you get coronal mass ejections. As I said, when the flux tubes collapse and they blow the material away, this is actual physical material. It's charged particles. They actually have magnetic field, and it takes 2 to 3 days to reach the Earth. There are spacecraft out a long way away from the Earth. Some of them are between the Earth and the Sun. Some of them are just in big Earth orbits that there's almost always one in the direction of the Sun or closer to the Sun than the Earth. And they pick up these particles going by and they give us a warning. And the particles interact with the magnetic field. They don't go straight through because they are particles and they're charged. They cause geomagnetic storms, aurora. But the important thing here is, and I've had people say, but we had one of those coronal mass ejections and propagation got really good. Well, after things calm down, you still have all this extra energy and extra electrons floating around, so you can actually have enhanced propagation. And this is a tracking of a coronal mass ejection coming out of the sun and going out, and it hit the Earth. The Earth is a little yellow dot there, so the Earth got a glancing blow from that one. Okay, during low solar activity, there's fewer active regions. There's a lower number of CMEs. There's much lower number of flares, and the major driver of propagation disturbances and changes is a thing called coronal hole. The sun, the outer layer of the sun is called a corona. It's it's very hot, but it doesn't have much heat because there's not a whole lot of material there. But because it's hot, it's very hard for material from underneath to come up and go through it. And so you either need something like a CME to blow the material through the corona, or you need a hole in the corona that the solar wind can come through. And these were actually postulated from the fact that there were geomagnetic disturbances and there was nothing going on in the sun. Where were these things coming from? And they said, well, maybe the corona gets holes in it and solar wind comes through. And that's exactly what it was. Later, when you got above the Earth's atmosphere and you could look at the sun in ultraviolet, they actually saw coronal holes. And everything here that's sort of gray is looking through the corona, and the dark area is the hole. There isn't any corona there. And so the solar wind can come straight through without a problem. So let's take a look at the ham band. Let's try to synthesize all this and how it affects the ham bands. Below 10 megahertz, the D layer absorption is the driver. So 80 and 40 meters are mainly good at night, and they're not particularly good DX spans in the daytime. That's even on low solar activity, that's fairly true. Above 10 megahertz, whether the signal gets bent by the ionosphere and comes back to Earth is the driver. So you need the F layer density be high enough to bend the radio waves back to the Earth. So you get 20 and 10 meters are open in the daytime. 20 and 17 meters are sometimes open at night. When you get up to what we have now, where we have a high solar activity and high number of high electron density, you can sometimes get you can sometimes get 10 meters open at night, but it's still a little rare. At 10 megahertz, 30 meters, that's right where density, the absorption is becoming much less and refraction is becoming possible more effectively. So basically 30 meters is always open if you believe it. Of course, that's not true, but basically that's why they wanted the 30-meter band, is because it's open when other bands aren't for one reason or the other. The maximum usable frequency is low enough that it can get bent by the ionosphere, and the absorption is not high enough to take it out. So 30 meters was considered a very important band, and it was one that the amateur radio community tried to get in the radio conferences, and they got it. And it's I don't know how many of you use 30 meters. It's a little odd band, but it has that kind of results. That is, it's always seems to go somewhere. Now the E layer. The E layer is more important. Usually they say, and even a lot of other things, they don't deal with the E layer very much. They say, well, it doesn't have much effect. It's lower down, so signals don't go too far, and it's not that important. Well, during the 2017 solar eclipse QSO party, in which a lot of data was collected over paths, it was discovered that the major propagation for 20 meters was the E layer. So suddenly it seems the E layer is not something that rarely causes any propagation, but it's really something you have to take into account. It has shorter skip than the F layer, and as I said in the talk I gave on field day propagation, when the sun comes up and the E layer comes up and you start getting E layer propagation, usually before maybe F layer or after F layer, but sort of comes in as another layer, you can have your skip distance suddenly change. And that's because the E layer being lower will have shorter skip than the F layer. And that's something to keep in mind. But the E layer is mostly daytime only. It goes away at night for the most part. Now, sporadic E. This is an interesting story. 20 years ago, I would have said no one understands sporadic E. The sporadic E is small regions of charged particles which cause refraction at high RF frequencies, higher than you expect, over a limited geographical extent. Well, it turns out that sporadic E is caused by the weather. So if you can predict the weather, you can predict sporadic E. And in fact, SAMI-3, which is the Naval Research Lab prediction program, uses the Navy's classified weather predictions as part of its input so that they can get out sporadic E predictions. And this is important to them because, believe it or not, over-horizon radar on the East Coast is used to track drug runners in the Caribbean. So it's important to know if you have sporadic E going on for your paths for using over-the-horizon radar in the daytime. So, or even at night. So one of the major things in your really state-of-the-art HF prediction programs are weather. And you can actually get a propagation analysis from SAMI-3 by politely asking the Naval Research Lab for. They won't give you anything except the results, but it's only for things in the past that they can get weather data off of the weather grid, not predicted, because that's their classified weather prediction program. Now, the symptoms of this is a thing called red sprites. It shouldn't be surprising to you that if you have a thunderstorm out there and you get lightning coming down because there's a ground layer below it that's at ground, and you've got charged separation, and you've got charged particles hanging around up here, and they find their way down to ground themselves out. But it works the other way. You can go up. You've got these charged regions above the thunderstorms, and the charges in the upper area of the thunderstorm can go up. This was not fully recognized for a long time. This is a picture of a red sprite taken from the International Space Station. And you can see it's quite a ways up there. The weather is quite a ways below where that red sprite is. And you can see why they're called red sprites. Here's some more. Once red sprites there were always reports of red flashes at the very tops of thunderstorms. They were seen by aircraft. They were seen by early space craft, but the actual color and everything else wasn't. And also, they were very short, and most of the spacecraft, for example, were not set up to take short exposures. And the result was that while they knew something was going on there, they didn't realize how widespread it was. Well, once these things got understood, You have storm chasers now trying to take pictures of red sprites. And there, if you go on the internet, there are pictures of red sprites all over the place. They are not rare. They happen a lot. They happen anytime there's charge separation in the atmosphere, which means you don't need a thunderstorm. You just need something that's causing charge separation, which can be something like a very high wind, upper air wind that causes friction that separates the charges. So they occur, and they're fairly common. And storm chasers love to take pictures of them. But this is electrical charges going up to the D layer and E layer. The top of thunderstorms is about 25 to 30 kilometers. The bottom of the D layer and E layer are about 50, so there's quite a bit of separation there, but it's lower density air, so the charges go through it a lot easier. It's like when you evacuate a tube and run a charge through it, you get a glow. And so you get these huge discharges that charge up the E layer and cause sporadic E. Aurora is another interesting phenomenon. They're very complex, and they were studied. There were lots of people, particularly up in northern latitudes, who studied aurora, but the money came when the Northwest Passage started opening up, and commercial interests were thinking about sending ships that way, and navies were thinking about having to protect the ships going through the northern passages. And so money started hitting the scientific community to figure out more about aurora and how they can be used. They're caused by charged particles from the sun interacting with Earth, just as we've been talking about. They spiral in the Earth's magnetic field and drift north or south. And they can only go so far north and so far south. And this is a little hard to see, unfortunately, but the charged particles stay around the mid latitudes of the Earth. As they get near the poles, the magnetic field gets stronger as it comes in, pinches in at the poles, and that causes the spiraling to get tighter and tighter and tighter, and you get a phenomenon called magnetic mirrors. And what happens is the particles can't go any further, and they start going back the other way. And so the particles tend to stay between a certain north and south magnetic latitude. But a strong enough particle can come in down through that and get down to the point where it hits the upper atmosphere of the Earth, which is essentially the ionosphere. And you get, this is just sort of going over the whole thing again. It's focused on the poles. And when they get low enough, when they have enough energy to get low enough, which is why you get aurora when there have been solar activity, because you've got the higher energy particles coming down, they get further before they hit that magnetic mirror, and eventually they get to the point where they hit the Earth's upper atmosphere and start interacting with the atmosphere. And you get a ring where the particles are interacting with the upper atmosphere. And this happens to be around the height of the E layer. And this is a more common way of looking at them. This is the actual, where aurora might be visible. And it's centered, as you can see, on the Earth's magnetic pole, because of the North Magnetic Pole. And you have this area of charged particles, which are acting like an enhancement of the ionosphere. But there are some things that are different. the particles are coming down. They are ionizing a column of the ionosphere, not a shell like the rest of the ionosphere. That means that your active area is tilted with respect to the surface of the Earth, which means that your refraction and absorption are different. And the guys up in the north in Alaska and northern Canada, they're really into this stuff. They'll sit there and they'll tell you the ionosphere above us isn't like anywhere else. And the reason is because of this tilt. Also, because it's being fed by the material coming from the sun, which is clumpy, it isn't coming smoothly. It means that sometimes it's worse and sometimes it's better. And that means the absorption goes up and down. Also, the way the path changes, you get multipath for one thing, and you get what we call auroral flutter. And I imagine most of you have heard of auroral flutter at one time or another if you've been on HF for any length of time. And that's when you get aurora in and your path or the path of the signal you're listening to is being affected by auroral propagation. Okay, so that's all the different kinds of HF propagation. So let's take a look, let's synthesize the whole thing by activity level and frequencies and stuff like that. In lower solar activity, the F layer is less dense, so the higher frequencies are less likely to be refracted back to Earth. And 15 and 10 meters are only open in the daytime, if then. And some of you may remember at the last minimum, which was very minimum, 10 meters almost never opened and 15 meters was a bust. The E layer is much less often in play because you don't have the high energy material, the high energy radiation coming down to ionize it. And the D layer has lower absorption for the same reason. And that means that 80 through 30 meters has more DX and 80-40 meters opens during the day instead of just at night. And right now we're not at low solar activity, but some of you may remember 5-6 years ago when we were. High solar activity propagation is the opposite. The F layer is more dense. You get higher frequencies are more likely to be refracted back to Earth. 15 to 10 meters is open in the daytime and sometimes at night. And lately, 15 has been open at night. I don't think 10 has been all that open at night. We may need a open every once in a while. 10 is open. We need back in 1959, which was the highest solar cycle ever. 10 meters was open all the time. 17 and 20 meters are open 24 hours. The E layer is much more in play, and the D layer has higher absorption. And so 80 and 40 are never open in the daytime. And you may notice that now. You get local 40 meter. I mean, during the Virginia QSO party, you know, here in Northern Virginia, we could talk to people in Southern Virginia, but you're not going to go much further than that. And if you're going to do other states coming in, if you're going more than West Virginia, North Carolina, Maryland, and Delaware, you had to go to the higher frequencies in order to get those contacts. So what do you look for when you're trying to figure out what the propagation is going to be like? The first thing is sunspot number, which is a poor number to characterize the solar activity. There's variable sunspot numbers for the same kind of activity. It isn't the best. You really have to use a smooth number because it goes up and down, which it's mostly noise due to the way they measure it. And it isn't exactly the world's greatest measure. Unfortunately, the propagation programs available to most hams all use sunspot number. And there's another gotcha with sunspot numbers, which I'll mention in a little bit. Solar flux index is much better. Solar flux index is measured by radio telescopes pointed at the sun, at the whole sun, and measuring the total flux coming from the sun. And that goes up and down with the solar activity. And it's much smoother, it behaves much better, and is a much better indication, particularly of radio propagation. And the lowest number for that, by the way, is 65. We used to say 67, but last solar minimum, it went down to 65. And the history of the solar flux is really interesting, but I'm not going to go into that here. I mean, of measuring the solar flux. And the third major number is the K index, and that measures the amount of geomagnetic activity that's going on. There are various K for different latitudes. You use the so-called planetary K, KP, to get an idea of the whole Earth. After all, we're sending signals all the way around the Earth. The K index, how I like to characterize what the K index helps you is that if you have a low K index and there's no disturbance in the ionosphere, it's like having, and again, bad use of terminology, but a mirror, a flat mirror, and where you hit the mirror, it comes down on the other side and you can predict it pretty well. Having a high K index is like using a mirror ball. And you can't tell where that signal is going to end up. You can't tell whether it's going to make it anywhere at all, because it may bounce around and not get out, if you will. And it's just and when it does come down, the signal does come down, it's going to be spread out over a much larger area, and it's going to be a lot less useful for communications. So K index is important. There are other things to look for: the number and orientation of active regions. Are they facing us? Are they complex or simple? And that basically you have to go to the people who put out these studies of the active region, monitoring of the active regions. They'll tell you whether it's complex or simple. Is there a coronal hole pointed towards us? And then the last thing, which is often overlooked, is the direction of the magnetic field in the incoming solar wind or solar particles. If the magnetic field is in the same direction as the Earth's magnetic field, or has the major component of it in the same direction in the Earth's magnetic field, it's like putting two magnets with north poles together and they repel. So the material tries to come in and it has a lot harder time because the Earth's magnetic field's trying to bounce it out. If it's anti-aligned, that is, if it points south, which is negative, then it's the opposite. It's welcomed in. It's attracted by the Earth's magnetic field, and it gets sucked through and causes a lot more damage. So the solar wind will more likely to have an effect if the Z component of the magnetic field, which is usually given as B, capital B, Z being B being the magnetic field and Z being the Z direction. So if the BZ is positive, a solar wind is less likely to have effect. If the BZ is negative, then you get more of an effect. And this is my favorite place for going for information. This is Solar Ham by VE3EN, I think, up in Canada. He got pissed off at the way the present administration disliked Canada and shut down his website a few weeks ago. and said, I'm not putting up with this. And it was off the air for about a week. In the meantime, a lot of people said, you can't do that. We like it. And they offered to help him with it. And they convinced him to put it up online, and he got help. And so it's undergoing changes. It's a little better, has a little better graphics now, and you can see where they're going with more readability and better handling of the information. So it doesn't look exactly like this right now, and it's changing quite often as the new guys actually spend a lot of time bringing it up. And I might add, most of this stuff is automated. It just goes out and grabs it from different sites, mostly governmental sites around the world, and then presents it in a single page, or actually a couple of pages. And it's actually a very good place to just look at and see what's going on. This is a plot of the Z component, and you can't see it. That's useful. This is the Z component of the magnetic field. The top part is the Z component of the magnetic field, and it's red. It's dark red, and you can't see it. But if you go to Solar Ham or somewhere else and find this plot, this is from the Space Weather Prediction Center, and you find this plot, the top plot is the direction of the magnetic field on the sun. And if it's positive, that is above the 0 line, then it's positive, and you're going to have less interaction with the with the ionosphere. If it's below that line, then it's going to have more an effect. And the bottom ones, if you watch the bottom plots, they will occasionally spike as material comes in, and you'll usually see either the BZ will either go south or north when the spike occurs, because it's indicating which way the magnetic field is with them. I'm going to go to the end here. Where are we in the solar cycle? Where are we? My standard comment is that we will know when the peak of the solar cycle has occurred 6 months to a year after it occurs. And you'll know when the sunspot cycle is at minimum 6 months to a year after it reaches minimum. There is no way to predict it. The predictions for this cycle were essentially a total continuum from the date over several years, and the amplitude was from 0 to 300 from the different people making that prediction. So take your pick. Somebody was right, or is going to be right. Well, right now, we're on the way up, or actually we're sort of leveled out. Now, is that a real level out, or are we here? I've seen both. I've seen predictions of both. As I said, we'll know 6 months to a year after it occurs. The one thing that is good, though, is we're a lot higher than the last one. And this, I'm going to show you some plots of historical sunspot cycles. The first is sunspot number from 1750, when the sunspot observations became reliable, and I'll show you why. And the second plot is a reconstruction of cycles before 1750 and continuing on, using sunspot groups rather than actual sunspot number, because basically, because the telescopes were so poor, whether you had one spot or multiple spots was hard to tell. And then prediction program, the present sunspot number system got revised 3 years ago. And the most most of the sunspot, most of the propagation prediction programs that hams have access to use the old sunspot numbers. So you have to sort of be aware of that the sunspot numbers that you're using today are higher than the sunspot numbers that the propagation programs were designed for. Okay, here's the solar cycle progression from 1750 to present. You can see there's quite a bit of variation in amplitude. There's also a little variation in onset, whether it's goes from 10 years to 13 years. If people try to analyze this cycles, and right now it appears to be stochastic, that is random. And as you can see, we're doing much better than the last sunspot cycle, but we're nowhere near the previous cycles. And here's the sunspot cycles going back as early as they think they can determine the number. I want you to notice that the red is the original numbers and the blue is what they've done in the subsequent years, where they've found new records from the early part. And as you can see, the ability to track sunspot groups got very good in the late 19th century. Before that, there's a bit of a divergence. And as you go further and further back, the divergence gets worse and worse. So the period from 1650 to 1725 is the Maunder minimum. It's still there. It's not quite the zero that it was, that it's been said to be for since it was rediscovered in the 70s by John Eddy. And but the other thing I wanted to point out here is if you can see, the reason why 1750 is the beginning is because if you particularly look at the red, there isn't much indication of an actual cycle before about 1750. So modern, and you'll see that here, the numbering system, which is hard to see in that forest of lines, it starts 1 at 1750, 2, 3, 4, 5, all the way up to 25. So basically, the sunspot cycle counting system starts in 1750. That's it. That's what I have. And I hope you got some idea of why propagation is the way it is.